Calcite is a mineral that can form crystals like this. This strange phenomenon is happening because this crystal somehow has two different indices of refraction. How do we reason about what's happening? First, a little chat about light. Light is an electromagnetic wave. It's an electric field that oscillates in both time and space, emitted from an atom or molecule. It is a flow of energy. If this is one such emission of light going into the screen, we can picture its oscillating electric field like this. The direction of oscillation is called its polarization. This is a vertical polarization. Just about every light source emits unpolarized light because, as the Wikipedia article states, it's produced by a large number of atoms or molecules whose emissions are uncorrelated and generally of random polarizations. Note that by linear superposition, every oscillation can be looked at as having a horizontal component and a vertical component. Meaning that unpolarized light with equal power in all directions has one half of its power polarized in one direction and the other half polarized in a perpendicular direction. What make crystals crystals are the amazing symmetries in their structure. We can draw calcites like this, a rhombus. As a beam of unpolarized light passes through, its randomly oscillating electric field interacts with and disturbs the ions in the crystal. We can draw those disturbances like this. What's happening is small oscillating electric dipoles are being induced in the ions by the unpolarized light. Other beams will do the same thing. I hope it's apparent that the two vertical ions will ultimately oscillate in the vertical direction only, as any horizontal oscillation gets cancelled out. In the same vein, the two horizontal ions will ultimately oscillate in the horizontal direction only. In other words, unpolarized light traveling through the crystal will create two perpendicular oscillations. As mentioned earlier, we can look at unpolarized light as the sum of two perpendicular polarized components. The vertical oscillations from the ions will interact with the vertical component. It can be shown that their interaction results in the slowing down of the oscillations in this component. The horizontal oscillations from the crystal will interact with the light in the same fashion. However, these ions are different and further apart than the vertical ones, and so this component will be slowed down in a different way, to a different speed. Because the speed at which light travels through the crystal determines its index of refraction, we have a different index for each component. And so our unpolarized light beam traveling through gets refracted as two polarized light beams of equal power, each polarized perpendicular to the other. Crystals that behave this way are called birefringent. Diamond, on the other hand, with its famous cubic structure, is not birefringent. How the structure affects the horizontal component is the exact same as how it affects the vertical one. The two components remain together as they travel through the crystal. Just a few more things. I've drawn our structures in 2 dimensions, but of course crystals are 3D. Calcite is actually like this. Note that the crystal has one longer axis, and the other 2 are the same length. These 3 axes make an ellipsoid. In this case, it would look like an American football or rugby ball, and it represents the indices of refraction for a beam going right through the center. I hope you can see how in the case of our diamond, this ellipsoid is a sphere. If we rotate along this axis, the indices of refraction for our beam remain the same. If we rotate along this axis, the values remain the same, and one beam will rotate around the other. But if we rotate this way, so that we're traveling along this long axis, the crystal structure will appear cubic like diamond. The indices of refraction will be the same. In this orientation, there will be no double refraction. And so double refraction will happen in a birefringent crystal as long as our light beam is not traveling directly along this axis. Since there is one such axis, the other two being the same, we call this a uniaxial crystal, and this axis is called the optic axis. Finally, what about when all three axes are different lengths? We'd be dealing with a biaxial crystal in that case, with 3 indices of refraction. Our ellipsoid would look like a flattened football. It's a more complex situation, so all we'll say about it is that biaxial crystals with good optical properties are hard to come by, and that the great Irish mathematician Sir William Rowan Hamilton figured out, without the use of experiment, that the resulting beam would not be some sort of triple refraction, but a cone of refracted light. I hope this has been able to shed some light beams on what birefringence is and how it gives rise to double refraction. It's as if we're peering into the very atomic structure of the crystal itself.